Okay, so we're still doing derivatives, but they're asking this one in an unusual way, and the way we're going to approach it is going to change slightly in response. This is the first question they've given us that is not nicely written in a form y equals some function of x. We have x variables and y variables mingled together in an expression, and you can even have terms like x times y, so it can be difficult or impossible to disentangle the x and the y, and so we have to be able to handle them coexisting like this. So this is a good time to step back and take a bit of a deeper look at why we differentiate the way we do, and where this dy dx construct that we use for a derivative comes up. For starters, anytime you have a variable or an expression like x, its derivative, and this part is an axiom that we just have to agree on. When you have a variable x, its derivative we write as dx, the derivative of x. If you have some power of x, now two things happen. First, looking at this, we see that the power rule applies, and so we do the derivative following that. We do 2 times x to the 1. And now the chain rule says, now that you've taken care of that square, do the derivative of the thing that was inside it. And so technically the derivative of x squared is 2x dx. If you have 3x to the 5th, the derivative comes out to 15x to the 4th dx. Technically, no derivative is complete until a dx or dy or dt has popped out on the end of it. And so you do the power rule or the product rule or the chain rule or the quotient rule as required, and at the very end, whatever your variable is, the derivative of that variable is going to be the last piece that you write. That's just an extension of the chain rule. If you have y, its derivative is dy. If you have y squared, nothing's really changing. You follow the same rules that you would for x. The derivative of y squared is 2y, and then you get dy. So what this means when you have an expression with two variables in it, something like y equals x squared, and this is a step the workbook never shows, but it's really not that bad to do it. Step 1, you do the derivative of this entire expression. So on the left, the derivative of y is simply dy. On the right, the derivative of x squared is, well, power rule first, 2x, and then dx. And what happens next is we divide both sides by dx. This cancels. And this is what we've been writing for the last several lessons, is that the derivative of y with respect to x, in other words, the rise over run, what we think of as a slope, is 2 times x. Anytime you do a derivative like this, there's a step that they gloss over where you divide both sides by dx, and that's why we get this ratio. And it's also why terms containing x look like they don't have any d after them. It's because we instantly divide it away and make it disappear. Let's do that with another example. If you have y equals x to the 5, I'm avoiding quotient or product rule because I don't have enough room to execute them correctly. Left side derivative is dy, right side derivative 5x to the 4th dx, and then we divide both sides by dx. These d's cancel, and we get dy dx, in other words, y over x, rise over run, what we think of as a slope, is 5x to the 4th. This approach has a lot of advantages later on. If you're going to be taking more calculus in university, thinking of them this way will make some things easier to see, even though it's maybe not quite as quick as just writing primes. So let's see how this applies when we have what we call an implicit derivative, or implicit differentiation. We have an expression here with x's and y's in it. We must differentiate it, which means we must find an expression for dy over dx. So here's how that happens. Oops, y squared, sorry. When we differentiate this first term, x squared, what we get is 2x dx. When we differentiate the second term, we get 2y dy equals, when we differentiate 15, we get 0. Now, what the workbook does at this point is instantly divide everything by dx, which you can do. There's one version where you separate the dy's to one side and the dx's to the other. The version that they're using, and I guess I don't mind following that, is at this point divide every term by dx. And what happens? Well, these dx's cancel. And we get 2x plus 2y dy dx equals, and 0 divided by dx is still 0. So now we must solve this for dy dx, because this is our slope. How do we do that? We can take this 2x to the other side. 2y dy dx equals minus 2x. And then we divide both sides by 2y. And we get dy dx equals minus 2x over 2y. Divide the top and bottom by 2. And there we are. So what I like about this method is that it treats x's and y's and t's and every other variable equally. We don't have to explain how come x's don't seem to have a derivative like this, but y's suddenly spawn this dy dx thing. The truth is, we really are treating every variable the same, and every variable, whether it's an x or y, pops out a d at the end of its derivative. We choose to divide by dx because we like to think of these as a rise over a run, because that's what we associate with slope, and slope is a useful measurement for us. So at the beginning, every variable produces a derivative in the same way. We'll see that in future examples too.